Okay, so hello everyone. Thanks again for being here today. I'm excited because today is the second chapter of this online tutorial related to inversion codes and radiative transfer in general. And today we start with RH, radiative transfer code. I will probably say it several times, not only today, but in the following sessions. I think RH is a really good code. So I'm really happy to be able to introduce it to you. But at the same time, it's really a very difficult or complex code. So please ask any questions that probably I may not be able to answer, but Han is here, so he will just jump in and will help us. But in general, I think spending some time to just learning how to use RH is going to be very useful for everyone. Even if at the end you just use design, it's good to know that RH is so capable that you can do a lot of things. So then, yeah. So let's start. And just as a new thing, I started the count on day 1 for RH. I think I will do it this way. So we had 12 days for SER, and probably we will have a similar amount for RH. So we start on day 1 today, and then we will do the same with design. So sorry. So in today's course, what we are going to do is we will learn the basics of RH. I would like to show you how to install it very quickly, or at least how to compile it. Then we will run just one example of a synthesis. And then the goal is to understand the general concept of the code, or what is needed to run it, and what information you can get in a general and a broad way. And then in following sessions, we will start covering specific files and configuration possibilities. So then you can learn step by step how to run the code and understand what is the implication of different configurations or different assumptions. And also, after running the code, we will have several ways of analyzing the results. We will start with the analyze tool, that is an interactive tool that Han developed, and it's really complete. So we will cover a bit the basics, but my advice, and I will say it later on, is just try to play with it, try to go to the different options and try to understand what is plotted or printed, because then you can get a better feeling of what we are computing with RH. And and then I will also show you a different way of just reading the output, so then you can make operation with them. That is something that we will do later when we cover a larger set of profiles, but we will cover both today. So then the first thing that we should do is to download RH code. The source code is in GitHub, so you can just go to the web page and download it. It's updated. SER is not so updated, but this one it's up to date. So the version that I'm using is the one that is in GitHub, and in case we add new changes because we find any bugs or something like that, I will update it, and also Han will update GitHub. In the same web page, you can have the manual of the code. I think the version is 2016, so so that is, but it's fine. If there are new things, we can add it or just explain it on the course. So I also added the source code and the manual in the Dropbox folder that we will link to during the course, just in case you want to have it there. But you can download it directly from GitHub. It is true that, as I said in the beginning, I will try to make these tutorials relatively simple and focus more on how to run the code and trying to understand how the code works, instead of really focusing on the equations and the theory behind. So I will try to do the same here. So in that case, I really recommend you to at least check the official publications so that there Uitenbroek 2001 and 2003. And also maybe it's useful if you just check also the review from Jose Carlos and Basilio in 2016. And for example, you can compare figure 2 and figure 3. They are, I put it in appendix of this presentation. So just to have an idea of the difference between solving the radiative transfer equation and computing Stokes spectra in LTE and non-LTE. So just give it a quick look and also try to read the papers. So just as a general idea, RH is a numerical code that solves the radiative transfer equation under non-local thermodynamic equilibrium. We can call it non-LTE from now on. It's you can see it as a step forward from SER in the sense that the populations that we get and consequently the profile that we get from that, it's in general more accurate, mainly for the lines that are sensitive to non-LTE. So as a reminder, in the case of SER, we assume that the spectral lines are described in LTE. So the populations of the different levels involved in a given transition are just solved from the Saha-Boltzmann equation, and they are basically dependent on temperature. In the case of RH, this is done differently. The diagram is at the end, but just I will probably get to it later. But we need to compute the atomic populations solving the statistical equilibrium equations. And after that, we connect this to the radiative transfer equation. And then we start iterating with a loop where we change both populations and the radiative transfer equation solution until we get a solution that is compatible between the both systems. And then we get what we said as the code converge. And then we have a profile. So it's a bit different, and probably during the course we will get into details. But today, just think as we are going a step forward, because some of the transitions that are very interesting for us, for solar physicists, that they need to be treated using non-LTE. The code also RH also adds additional options. Sorry. That SER cannot offer. So for example, in the case of SER, we have a column by column. We solve the radiative transfer equation column by column. So it's like a 1D or 1.5D solution. But in the case of RH, we have the option to add a 2D or even a 3D computation. That means that we are also taking into account radiation and the effect of having pixels around the pixel of interest, but this is very important mainly for non-LTE. And also something that is very important for the lines that we are also interested on examining or analyzing is that the code can work on the so-called complete redistribution, or it can add the partial redistribution assumption. And this is really critical for some spectral lines, in particular resonant spectral lines like calcium 2 H and K in the blue in 395 nanometers, magnesium 2 H and K in the 2000 Armstrong regime, and Lima and alpha that is even in the UV regime at 1200 something Armstrong. So then the code is really more accurate for synthesizing these spectral lines. So for this reason, that set of extra options makes the code really versatile and powerful. And as I said before, I think it's one of the most capable codes that we have nowadays. And this was the main reason why we choose it as a seed for design. So we needed to have an accurate estimation of the atomic populations, and we also wanted to tackle or to make the inversions, including partial redistribution effects, and RH provides that in a very accurate way. And I think this also is the reason why STIC, that is also a very good and powerful inversion code, is based on RH. But at the same time, this also means that It has, I would say, a relatively steep learning curve. So you have a lot of options and a lot of complex things that you need to configure. So then it's not so easy to just start using it. But as I said before, here we are going to go step by step, covering most of the things that I believe are needed for understanding how to run the code and understand the output. So don't be afraid if you try to run it now and you see that there are multiple options and you don't understand exactly what they mean. Okay, and yes, an important thing is that if you know better RH, then means that you will be able to understand better how to run design or stick. If you use it in the future, you will understand more how things are done inside the code. Okay, so then let's start today's class. Let's go back. Yeah. Okay. And then you're seeing the editor. I was using Kate for the CERN course, but it suddenly crashed and I was not able to manage to make it run. So now I'm using a new editor. It's called Visual Studio Code. So I hope it's working and you can see things. And I will try to get used to use it as the next sessions will come. But I think it's working well, and also the terminal is integrated, so it's I think it's easy for running and see what is written in the script. Okay, so then the first thing we are going to do is that so just mention that this is the RH folder, so you will have access to it, and we have day one. So here we will have figures and the presentation, and the source code and the manual are here, okay, with the version that we are using now. So then so you download the RH distribution, sorry, you download the RH distribution and then you put it in your computer and you unzip or compress the file. So then the first thing I recommend you to do, in this case, just I will make clean because it was already compiled, so I was using it. So the first thing is just go to the RH folder and just type make, and then the code will start compiling. In principle, with most of the general compilers should work. So if you have any issue, just let us know. But then the only thing you need to type is make, and then inside there are several folders. But today we are just going to go to RH F1D. That is the 1D version of the code. That is the one we are going to try today. And then again here you can type make, and then it will compile everything. So then the code in principle is ready to be run. Okay. So then inside, so the way you can run the code, it's you can put the examples that you want to run anywhere, but usually what I do is that in the same RHF1D folder, I create folders with examples, and then there I run the code, and then it's usually easier this way because most of the files are by default ready to do it this way. Otherwise, you have to change a lot of paths to different files. So I recommend you to start playing with different examples, just putting the folders where you run the code here in RHF1D. And then today we are going to focus on this one, example one. Okay. So inside there are several files that are the ones required for running the code. We will cover them, but we will go through them just using this IDL script. Okay, so then this is the one we are seeing now. So then I put a lot of text in this version. I think it's easy to read them and to follow them while you are running the code. So let's go through it. The first thing is that today we're going to do a very simple example. We are going to compute in non-LTE the calcium 8542 spectral line with polarimetry, and just that, basically that. We will try, as I said, to understand how to run the code, and then all the things, small things that you need to configure or you can play with to adapt the run for your interest, they will come later. So the first thing that you need to know is that there are 5 main input files. They are atmos.input, keyboard.input, curux.input, molecules.input, and ray.input. So these ones are the ones you need to configure for a specific run. And we will go through them very quickly now. And then when you run the code will provide various or a multiple set of files that they have a given name, and then the extension is .out. Okay, and for example, you can have atmos out or atom, the element and .out, geometry, opacity. We will cover what they mean or what they contain and what is their format in later sessions. But essentially, you have a set of input files, and then the code runs and then create a lot of output files. Okay. So then, yeah, I said here that just try to compile and then put this folder that I will put the file in the Dropbox folder. Just put it in your RH1D folder and try to run it. Okay. So then just let me go to example 1. Okay. So then, so then the first one that you need to configure is the atom. So in this case, you have that there's a list of lines here. You first have the number of different elements that you have included here. So this number should be the one and the same as here. If you remove some sentence here, then please update the previous one, otherwise the code will complain. And then the main thing is that usually we will solve multiple atoms, but we will do it in 2 ways. The passive way is that the atoms are used for computing a more accurate background opacity. And then in the case of active, are those atoms where you want to have an accurate estimation of the atomic populations of the different levels involved in each transition, and it will provide a spectral line also. So in this case, those atoms, they will not provide any spectral line, but they will participate, or they will have an impact on the background opacities that at the same time will produce a better profile for example, for this case. So then this means that they are in a reference folder inside RH that is called atoms, and then the code will read them. And then you can see that this one has no dots, and it's because I put it in the current example folder. So you see here, I put this one in this folder. And this is because usually you change the atom. For example, if you want to have more wavelength points, or if you want to have them distributed in a given way, so you start playing with the atom model. So then, in that sense, sometimes you make a wrong choice. It's better to have a copy that is good and change in this folder. And I recommend you to copy the one that you are going to play with in your example. So then if something gets wrong, or if you did a change and the results are not reasonable, then you can always go back to the default version and check what could be the problem. Okay, later on we will check what this different sentence means and what is included here, that is in general the population. But the important thing is, when you want to run a specific spectral line and you have the atomic model needs to be set here as active. So in this case, you see that we have a calcium-2 model that is set as active, and this one will be the one producing the calcium infrared line. So then the next step is molecules, and here is basically the same. So you have a set of molecules that are also in a reference folder inside RH, and then if you are interested in a transition that is defined inside those models, then you just set it as an active, and then it will be computed. But in general, they are used for having a better estimation of the background opacities, and we usually have them all in passive. Okay. So then we enter in probably the main file, that is the keyword.input. You can think of this file as a control file or the troll file that we had for share and we will have for design. And here we define a lot of things. In particular, we defined how many iterations we want to have, where are the abundances, or where are the things. And it's a very long file. Is this one, and you can see that there are a lot of options. This character means a comment, and then the rest of the things are instructions for the code. And as it is very long, we will dedicate probably just one class only for covering it and understanding what are the meaning of most of the things. There are comments, so maybe you can have a feeling of what they do, but sometimes is better, or it's not so clear what are the options. So don't worry that we will cover them. And one of the things, and important things that we include in this instruction file is the atmosphere that we are going to use. I put a note here that for historical reasons, the RH atmosphere is divided in two files. So we have the thermal part that it will go in a file called name.atmos. So in our case, is the first entrance that we are using a FALSI model. And this model, we will see it later, but it contains essentially temperature, electron density, microturbulence velocity, and populations of hydrogen. And the information of the magnetic fields goes in a different file called something .b. That is, it's indicated to the keyword file in a different line. So the important thing is that there we tell the code where the atmosphere is, and the code can read it. And yes, we will enter in details of the atmosphere, how to create it, and what are the units and everything later on. Just as I said, today we have a reference atmosphere that is from Fontella et al. 1993, and I created an additional magnetic field that is constant with height, and I think is 45 degrees inclination and 70 degrees. So just a reference magnetic field to have a polarization profile later on when we check the results. But in future classes, we will learn how to create the files itself. So again, here you will have things like where is the abundance, or different number of rays, or where is the atmos.input. So later on, we will check that. Okay, so then we can move. So yes, as I said, we will cover this later on. Just let's have an idea of what are the files that we need for running the code. Then the other one, it's the third, I think, it's ray.input. So the idea is that when solving the non-LT problem, RH will solve the radiative transfer equation for a given set of heliocentric angles. And this is defined in the keyword.input. But sometimes the set of heliocentric angles does not match the one we are interested on. Maybe you are interested on the center, or maybe your observation is at mu 0.67, for example. So if you want to compute that specific heliocentric angle, then you put that value in ray.input. So here you have, now I'm telling the code that I want to compute the Stokes profiles at mu equal 1. But if you want 0.76, for example, then you just put it here. So it's a way of telling the code that after all the process, you want an extra step where you want the specific profiles at that heliocentric angle. And this is through ray.input. Then the next file is kurux.input. So the idea is that as we saw in the previous in previous tutorials when we were using SER, the Kurux database is really complete. There are a lot of spectral lines there, and then RH is offering the users to just take those lines and put it in a file, and then the code will be able to just read the entrance that you have there and compute the lines in LT. So then this is really, really helpful because you don't need to do it by hand as we have to do it for SER or design. And you just need to select the lines you're interested on and then copy them in a file. In this case, kurux.input, what it's saying is where the file, just a text, is located containing those transitions. So I will show you how to create that file. But the idea is that here we are just telling where the file is, and you can have several entries. So if you have lines in the blue and in the red, and you can have them all in one file, or you can have several files. So the idea is that today we don't have anything. I will just not use it today, but the idea is that you can just copy those lines, and you can go to this example and check how the lines are located there. And then the code will read it and go through it and synthesize the stocks profiles for that line. I just add a warning, and is that in general, RH was designed to work under LS coupling. So before, if you provided a set of lines and some of them are not defined under the LS coupling scheme, then the code will jump those lines. So it means that it's really useful because you just copy a bunch of lines and you put it there and the code will work, but you have to check that they are in the proper format. And we have been updating RH to accept different formats, but sometimes the lines are very, very complex and they may not work. So the idea is that in the future, we will dedicate also one class to learn how to put the lines in the Kurux file, but also check which ones need to be slightly updated to then be properly computed with the RH. Okay. So then basically at this point, we have everything ready for running the code. So then the only thing that you need to do is to just type this in a terminal. But as we are inside IDL, we need to add this. But basically, just typing this, the code will run. So then I just compile the script, and then you will see that there's a lot of things going on. And then we will cover this in detail. But basically, the code looked for things, did a double check of the atoms, then the molecules, and then it's saying something about the wavelength points that it's going to use. And then it started doing the iteration. And this is what I said before, that now the nullity problem requires computing, so solving the statistical equilibrium equations, then using that for feeding the radiative transfer equation, and then going back to check that the results from the radiative transfer equation are compatible with the populations, and then iterate the process until you find a good solution. So then you see that there's some value here that we will learn what does it mean in the next session, but you see that it's decreasing. One order jump here and then slightly decreasing, and then it goes to -2. So then other jump, and then finally it gets to a given value, and then here it stops. So I'm just as a reference, I'm telling the code that my threshold is 1 × 10⁻⁵. So then the code is iterating until it gets below 1 × 10⁻⁵. And then it assumes that it has converged, and then it stops and saves everything. Okay, so then we have just computed a profile in non-LTE with polarimetry. And then this is what I have said. Yes, so then you can take a look at what I said here. And then, as I said before, for this specific case, I also want to have the profiles at mu equal 1. So then this is a second call to RH, where we just say solve ray, that it means it reads what is in ray.input, that is heliocentric angle equal 1, and then solve the radiative transfer equation for that ray. So then if I do this, it does something and it seems to work. Okay, so then at this point, we can set that we have everything ready for checking the results. And here we basically have two ways of doing it. I think the first one is the one that you should probably spend some time on because it's really helpful and I think illustrative. But then the second one will be the one that we will use later on because we need to do it for a lot of pixels. So it's easy to handle a large cube if you just save everything in memory and then plot it with in a different way. So, but let's start with the first one that I think is the one that you should work on these days. So I just load this environment. I think probably the first time it will ask you something like saving IDL file. So just type yes when they ask you. But in my case, I just do this and then it says compile module RRH. So then at this point, you just type analyze and then it will pop up this window, okay? And then here you have multiple options. So then, for example, you can say, okay, let's check the atmosphere that we are using. So then you just type there, and then you will see that it's a bit difficult to read maybe, so maybe in your computer it will be easier, but the code is plotting the height in this axis, and then this is mass column, this is optical depth, temperature, electron density, hydrogen, microturbulence, I think, and then you have other options, and you can set, okay, which atoms are active, and then in this case it's calcium, and then it computes some things. I like this one, that is a term diagram, so then you can see how the different levels are defined in your atom and how they are connected, and you can see that those two levels are related with the calcium H and K populations with the ground level, and then the infrared ones are from in this direction. So then I think this is very illustrative. I think you can play, you can add different atoms. And the important thing that to try to keep in mind is that what we are doing in this with RH better than SER is to have the populations between those levels with much more accuracy. So it means that the transition produced between them, it's also much more accurate. Okay, so then I go back, I also go back, and then you can go also to intensity. And for example, you set emerging intensity, and you have here. This is also interesting. Usually RH will compute the full spectrum from the blue to some point in the red. But the grid file, so the number of wavelength points, it's not uniform. So you will have more points on the regions where you have atoms active or where you have defined them. So in this case, you see that there's like a continuum, the continuum we expect from the blue to the visible and the red. And there's something here and here. And this is basically calcium H and K here and calcium infrared here. So then if you just type, for example, I want to see the wavelength from 853 from, this is in nanometers, 855, let's see. Okay, so then you have here the spectral line of the calcium infrared, the 8542 line. You have different colors. The blue ones are the ones that the code used when solving the non-LT problems. So then they correspond to different heliocentric angles. This is something that we will check in the future. But for this reason, so the ones with lower continuum, they are probably close to the limb, and the ones with higher intensity in the continuum are the ones close to the this center. And then you have this yellow that I think is the one that we computed in with ray.input. So yeah, and then I think you can also go to polarization and you said, okay, stocks V, and then here you can see that now it's keeping the same wavelength range, and this is stocks B for a calcium line, and again you have different profiles from the different projections used in the computation. Okay, so then please try to use it. There are additional tools and things that you can, statistics. So there's a lot of things here. So just try to play a bit with it and try to understand some of the concepts. If you have any questions, just let us know. But I think it's very complete and very easy to use at the beginning. So play with it, please. And then after that, the option that I usually use, and we would use, and mainly when we go to the parallel wrap, then we will not see the previous tool at all. So we will just have a cube of output data. So then what I'm going to do is to read the output files and that code generated in this folder. There's a routine for doing that. That is, in fact, used by the previous widget. That is readall.pro. I modified it. This is readall mod. What I did was just remove the last part to keep it open. So then, in my case, it worked. I think in your case will also work. I put it in the example folder. So the idea is that if I just run and use this routine, then the code has read a lot of things, most of the output. So then we will have ideal structures in memory that they are called geometry, atmos, spectrum. So for example, geometry, that I'm typing help geometry, and this is what you are seeing here. So geometry, it's telling us that lambda is the wavelength vector. So if you want to have the wavelength vector is spectrum.lambda. Okay, and then you have profiles that were computed in the 5 different heliocentric angles. Then you have additional things. Also, you can set, okay, help atmos, and this is again another structure that it contains elements, temperature, electron density, hydrogen populations. So everything that code is using for plotting the widget, you can read it this way. And this is what I do when I do a loop and I'm computing multiple profiles, for example, from a simulation. I do this and I'm just saving the profiles, and then I can keep them for analyzing them later. So then, just as an example, we can read the profile at heliocentric angle 1. So we can just say, let's continue. So then if I said help ray, so then this ray is the 4 Stokes parameters, I, Q, U, and V. And it's telling us also the heliocentric angle. So then if you just type plot, yeah, I did it here. So just because if I do it, it will not be as beautiful as this one. So here I'm plotting the wavelength vector, that is the spectrum structure with the extension lambda. Then Stokes I, that is the structure ray with the extension I. Then the second plot is again lambda or wavelength with the ray and the extension Stokes Q, and then U and V. Okay, so if we plot this, we will have something like this one. Okay, so it's essentially the same plot that we were seeing with the widget. So it means that we have access now to the profiles. So if we want to use them later for different things, or again, if we want to run this for multiple pixels, this is the way of saving the data. And you can see that they look reasonable. So this looks like a calcium profile. Stokes B, they are relatively okay. One thing is that this is the units that are provided by RH, and they are SI units. So they look a bit different than what we are used to. But the idea is that you can always normalize to the local continuum close to the wing, and then you will have it in the units that we are used to have in SER. Okay, and then as a next example, I do the same with an atmosphere. So now we are going to see this plot, and what I'm doing is plotting geometry.height. So geometry is the structure, height is the geometrical height, and then temperature. So it comes from the structure atmos, and then the extension is T. So it's a bit tricky at the beginning, but you will get used to it. And if not, just let me know. I know more or less which variables are in which structure. So I put it as a sample on purpose to just show you that you need to play with one or the other. But at the end, it's relatively easy to understand that this is electron density and this is field strength. Okay. Just also check that I'm changing the units. So this is in meters. This is in Tesla. So just try to also think about that when you are playing with the results. And also the important thing that we will go back to this later on is that the atmosphere that we are providing, let's check it. So in example 1, if you remember, we said that we are using FALC. The atmosphere that we are providing, it's in height. So we have a geometrical height vector in kilometers. Then we have temperature, electron density, velocity. And so this is the standard velocity, and this is microturbulence. But the code internally, it's also computing the mass column related to that atmosphere, and also the optical depth at 500 nanometers. So this is a really exciting thing, because it means that it will be really easy for us in the future when we have a simulation that in general are in geometrical height to compute the optical depth, because the only thing we need to do is to run the code. And we will see that this will be what we call conversion mode. And it's just running RH will give you by free the optical depth vector with a high accuracy, because we are including proper background opacities through large set of atoms and molecules and models. Okay. And then I finish usually the programs removing everything. This is just for keeping it clean. So if I type this and we wait a bit, so just let me remove these. Yes, this one. So just go back to the beginning. So this is everything we needed to run the code. So just as a summary, we had 5 inputs: atoms, molecules, keyword, ray, and Kurux. Then we had the atmosphere, the thermal part, and the magnetic field. We use one non-LT atom, that is the calcium one. And then we just run the script, and I put this read all mod routine there, just in case it doesn't work, or it's better to have it there. And then this is the script we use to run the code. And after that, the code will generate a lot of output files. But this is essentially what we need to run the code. And we will go step by step, covering each of those files and all the configuration elements related to them. Okay. So then I think this is basically what I wanted to show you as a run example. So before going to the final touches of the presentation, is there any question that you could have now? So no? Okay. Yes. Yes. That, I think, is that all right?
Yes.
Yes. Hi.
Carlos, yeah, I want to ask you something. This is not directly related to the main subject of the lecture, but I saw that when you show us that the stock 3 profiles of this line.
Yes.
So the there's some secondary peaks at the continuum
Yes.
in Stokes V.
Yes, so I think the line is a bit complex, but I would say that when we study response functions later on, it seems that this part that looks like Stokes B itself,
Yes.
it's the main contribution from the wings. And then you see that it's positive and negative, but then inside you have like a different behavior, and this is from the line core. And we will check that in detail, but it seems that the Stokes profile, it can be broadly saying separated in the contribution from the wings and from the core.
I see.
Yes.
Maybe this is because probably you have included the magnetic field, constant magnetic field all along your atmosphere, right?
Yes, but I think the main reason is that the line is sensitive to a large range of heights, and the temperature it has different gradients from in this range of heights. So when we see the response functions, we will see that they are a bit complex, and sometimes there's like a change of gradient between them, and this is basically because the temperature is also changing. But I would say that this should be the expected profile that you can have, where the broad wings come from the wings of the line and are sensitive to the photosphere, and this center part, very narrow, it comes from the line core and is sensitive to mainly the chromosphere.
Nice.
But I think, yeah,
maybe the easiest way to think of or to explain the shape, the precise shape of the V profile, is to think of the Stokes V as the derivative of Stokes I, and you see that the Stokes I profile is also not a simple Gaussian or Voigt profile, right? It has the knees,
yes.
and so all these little changes in gradient of the I with lambda change the Stokes V, and physically it just means that there's a mix between the magnetic sensitivity, the width of the profile because of the splitting in terms of Doppler units, and the absorption and emission of Stokes V. So it physically becomes very complicated. But the easiest way is really to think of the profile. When you see a complicated Stokes V profile, go back to the Stokes I and see that that probably it is complicated too.
Yes. I think you can see that in this way. So this is going smooth down. And this is what is making this smooth Stokes V.
Exactly.
But then you have a sharp change, and this sharp going down is the one that is producing this sharp Stokes V.
Yes.
Okay. Thank you. I've never seen this in the observations, but in the observations probably we just don't have enough resolution because these peaks are very small, right?
Yes. I hope that with the forthcoming spectrograph observing in the 8542, we will probably see these more and more. So let's wait a bit, but I would say that we should expect having this when we have higher spectral sampling. Okay.
Thank you.
Yeah, thank you. Okay, so any additional questions?
Maybe I can make two additional comments.
Yes,
can you put up the atoms.input file again, Carlos? And maybe you will touch on this later, but I think I would like to make it a little bit more clear about what passive, active, and so means.
Yes.
So on purpose, this is not called LTE or non-LTE, because it is actually possible to include non-LTE population numbers for an atom without having it active. So what you can do is to do, in principle, RH can calculate several active atoms at the same time.
Yes.
But what you could also do is to calculate one atom in non-LTE, store the population numbers in the pops.atom.out, and then read them in as all populations, where the initial solution, in this case, you only have zero radiation of LTE population, but you can have all populations as well there. And so the point of having passive or active is that when you have set active, that atom takes part in the active non-LTE update of the population numbers. Mm-hmm. If you set it to passive, the population numbers are not changed.
Mm-hmm. Okay.
But they're not necessarily LTE.
Yes.
And the other thing is that is maybe a little bit of misleading is that if you say, for instance, look at the oxygen atom, where it says the initial solution is 0 radiation. If you set it to passive and the pops that are not specified, are not there,
yes,
then actually it will use LTE populations for the background. It will not use the 0 radiation populations. So that's a bit maybe misleading, and that yes, needs to maybe made clear. But in general, atoms that are active and that you are not providing explicitly with population numbers are using LTE populations.
Yes. Okay. Okay. Thank you. Yeah.
And then the second with the molecules.
Yes.
Yes. So the molecules are not only used for the opacity; they also are used for to determine which molecules are used in the chemical equilibrium solution. For instance, if you would do a calculation of oxygen lines in a cool model, like in the sunspot model, mm-hmm, significant number of oxygen oxygen atoms would end up in CO molecules or OH molecules. Mm-hmm. And so that would reduce the number of oxygen atoms. And so that's why the molecules.input in general is there. Now, in each of these .molecule files, you can also specify line lists. And if you do that, you can include molecular lines in the calculation as well in LTE, or in some cases in non-LTE. Mm-hmm. And that's also, again, where the passive and active comes from in this case.
Okay, thank you. Mm-hmm. Okay, so additional comments, Han?
No, I think that's
okay. So then I think yes. So let's go back to the presentation. Okay, we can continue from here. So then today is a bit easy. So it's just try to copy the RH distribution of the code in your computer and just type make. Let's see if it just compiles and everything goes well, and then go to RHF1D and type make again and check that everything is working. And then just copy the folder that I will put in Dropbox today or tomorrow. Just copy it there and try to run it, the script I prepared. And let's see if it works. At least try to reach the point where you type analyze and it's working. And if you have issues, just let us know or use Discord and we will try to solve them. Yes, this is what I said. And try to play a bit with analyze tool. I think it's really capable, and at least for getting a feeling of all the things that the code is doing. Then next class, we will continue with RH code. I think we will move to the atom itself. So how to configure the atom and what are the different things inside the atom and what is the impact on the final computation. I will probably prepare an additional one, but depending on the time, I will see if we cover both or just one. But the idea is that we will try to go through these 5 main input files and all the sub files that are related to them to try to get a feeling of how to configure them and what are the meaning of the different instructions. Okay. Yes. And then it will be next week, next Friday. Okay, so yeah, I think that's all for today from my side. Is there any other question before I stop sharing? Okay, so then I stop sharing and I just quickly ask, how was today? So I think RH is a different, let's say, beast compared to SER, but was it okay to follow more or less the general concept and covering more or less the input files, and then slowly we will go through them? Was it clear or was a bit messy?
Yeah, it was quite clear, but yeah, it will become more clear when we will do ourselves.
Okay. Okay. Good. Thank you. Okay.
Yeah,
Okay.
it was very clear, Carlos. Thank
Okay.
you.
Thank you. Okay. Okay. So then, if there are no other comments, we can leave it for today. And I hope to see you next week. Okay.
Thank you.
Thank you, everyone.
Bye bye.
Thank you. Bye.